Okay, for this problem, let's take a look at the degree of freedom that this one has. So let's do it by looking at the motions. So you ask yourself, is it possible that something can move? And yes, body A, pin A, can move. It can go vertical. So you count 1 degree of freedom. So then you hold A and you ask, can something else move, not go limp, not break, not fall apart? And the answer is no. So the degree of freedom is 1. What this means is if you give me one position, I can find all other positions. If you give me one velocity or speed, one single dot term, I can find any single dot term you want. If you give me one double dot term, one acceleration term, I can find any acceleration you want. So depending on what is asked in the problem and what's given, it'll tell you whether you need a free body or not. For example, if you say that the acceleration of A is equal to, say, 3 meters per second squared, and I ask you what is the acceleration of B, you do not need a free body for this because the acceleration, because it's 1 degree of freedom, you tell me one acceleration, and you're asking for an acceleration, I can do this problem. If you ask me for, say, the velocity of B, and you're giving me an acceleration, then I can, if this is known to be a constant, if I can integrate it and take a derivative, whatever I need, then you can also solve this problem because you can solve for the acceleration of B and then integrate it. Now, if you only tell me the acceleration at this moment, there's no way you can integrate that. But anyway, you would not need a free body in a case like that. Okay, so suppose we change the problem statement. Okay, suppose I'm not going to give you these things. But what I will tell you is that, or what I want is, I would say, I will tell you the force that's applied to this guy. So I'll say there's somebody's got their hand here, and they're pulling this up with a force of, say, 100 newtons. Okay, so what do we have to do for this one? Well, just because forces are given does not mean that it's a free body diagram. But anyway, you do the same thing. and so you say, well, what is it that you want? I want you to find the acceleration of B, or maybe the acceleration of A or whatever. Okay, so can I do it? Well, there's 1 degree of freedom. That means if you want me to find an acceleration, you have to give me an acceleration. You're not giving me an acceleration, therefore I need a free body diagram for this particular problem. Okay, now one of the confusions that students ask is they say, now wait a minute, I know, for example, that the acceleration of B down here in the vertical direction is equal to 0. Isn't that a known acceleration? Well, these accelerations that you have to have, that be given, have to be accelerations along the freedom. So in this particular case, the freedom of this, when body A goes up, right, that's the freedom direction. So when that one goes up, this guy is going to move in this direction like this. Okay, so you need the acceleration either here or you need the acceleration here, one or the other. Just to kind of emphasize this, for example, the acceleration of A horizontally is equal to 0. So, you could say, well, look, I know 1, I know 2 accelerations. But again, these accelerations are not in the direction of the motion, so they are not the ones that you need. You need an acceleration along the direction. So in this case, if you don't give me either this one or this one, something along the direction, there's no way you can solve it. You're going to have to do a free body diagram. Okay. The other thing that you could be asked for occasionally is they could say, they'll give you 1 degree of freedom, they'll give you the force, and they'll say, what is the tension in the cable, or tension in the rope? Okay, so here what they're asking you for is they're asking you for a force. Whenever they ask you for a force, it's a dead giveaway that this is going to be a free body diagram problem. Okay, so that's how you can tell if it's a free body diagram problem. Okay, the next thing would be how many free bodies should you write? Well, here what you ought to do is you ought to count the number of bodies. Okay, how many bodies are there in this problem? I see two. There's a body at A and there's a body at B. So the question would be, should you put A and B together in a free body together, or should you separate them out? In this case, the acceleration of A is not the same as the acceleration of B, and therefore you should separate them out. You should have two free body diagrams. One of them would be the body of A, so this would be A. What are the external forces that are applied to it? Well, you have weight, so if this guy has a mass, he's going to be attracted by the Earth, so there will be a mass of A times gravity. There's that 100 pound or 100 Newton, whatever it is, pulling the guy up. Somebody has to be, holding their hand there doing that. A has also a rope, and ropes can only pull, so this would be, I'll call it R for rope. There'll be a rope force on there. And then you have two edges pushing on you, and in general, this thing could be shoved in there really hard. And so the right wall could be applying a pressure to this body, and also the left wall might be applying a pressure as well. So we'll draw it like this. And the reason I draw the left wall a little larger than the right wall is to make a point. The amount of force on the left and the right, if they're shoved in there really hard, say this amount right here, balances this amount over here. But there's more on the left-hand side. And so usually what people will do is, instead of drawing forces from both directions, they'll just say, well, one of the walls is a little harder, pushes harder than the other one. And so what they'll do is, instead of drawing these two, what they'll do is they'll just say, well, I think the left wall is pushing hard. I think the left wall is pushing harder. And so they'll just draw the force from the left wall. So I'll call this W for wall. Okay, for the free body of B. Okay, for drawing the free body diagram of B, start off with this one. He has a weight down, MB times G. The floor is exerting a pressure on him. We'll call that a normal, N. Maybe there's friction. If there's friction, the friction will oppose the slip. It tries to prevent it from slipping. So there will be a friction force here. If it's kinetic friction, this will equal mu K times N, the pressure pushing them together. If it's static, then we don't know what the friction force is. We'll just call it F. The other thing that is applied here is the rope. So the rope was called R. So in this case it has to be R because it has to be equal to the other rope. And it's in this case pulling straight out. So that would be the free body diagram of body B.